And to assist me in introducing the speaker, I have none other than Eunjun, who is going to help me. Go ahead.
Yes, the last speaker of the afternoon session is Seonghyeon from Ajou University. His title is Homology of real toric varieties associated with the Weyl groups of types E7 and E8.
Thank you very much. I'll give you $5 later. Welcome.
Hello. I'd like to start by thanking to the organizers for organizing this conference and for giving me the opportunity to present. So, in this talk, I will represent about the homology of real toric varieties associated with the Weyl groups of types E7 and E8. This is a joint work with Seonghyeon and Seonghyeon in Ajou University. A root system is a finite set of vectors satisfying these conditions. Among these conditions, the reflection in condition 3 is associated to each root, and it has nice symmetry. So we can think the group generated by these symmetries. So this group is called the Weyl group, and the set of hyperplanes perpendicular to each root separate the Euclidean space, and so each connected component is called a Weyl chamber here. So this is example of the root system and Weyl chambers of type A2. So here, the colored by gray is the Weyl chamber. As shown, the set of Weyl chambers in this complete non-singular fan, and this is the example of Weyl group and Coxeter group and Coxeter complex of type A. The Weyl group of type A is the symmetric group, and the Coxeter complex of type A is dual of permutohedron. The permutohedron is the corresponding fan of permutohedral variety. So because of that, so yeah, as I told before, the set of Coxeter complex in this complete non-singular fan for type A, it is not only for type A, but also for every type of irreducible root system. So in 1991, process suggests the toric variety over this fan, and he induced that this fan is smooth, and the real locus of this toric variety is called the real toric variety associated with the Weyl group of type R. So it is well known that the Betti numbers with any coefficient of complex toric variety can be easily computed if we know the combinatorial structure of the corresponding fan. But for real case, it's not. Because of that, I want to compute the Betti numbers, actually the rational Betti numbers of real toric variety. Remark that the fan associated with the Weyl group is corresponding the pair of this Cox complex and characteristic matrix, and the column of the characteristic matrix is the coordinate of each vertex in the coed lattice. So the above lemma says that the Y group acts on the Cox complex, and this action preserves the kernel of characteristic matrix. And this theorem says that there is G-module isomorphism between the real toric varieties associate the Y group and the summands of homologies of some subcomplex of KR, and this KS is induced by the elements of row space of lambda. Then by this theorem, we can compute the Betti numbers directly without the computation of whole toric variety, very huge toric variety. So the rational Betti numbers of real toric varieties associated with the Y groups were computed for all classical types A, B, C, and D, and for several exceptional cases for G2, F4, or E6. So there had been remained only 2 cases for E7 and E8. Then these numbers are, or the number of facets of Cox complex for exceptional cases. For G2, there are only 12 facets, and for F4, there is almost 1,000 facets, and for E6, there are almost 50,000 facets. But here, for E7 and E8, there are almost 3 billion facets, and there are almost 700 million facets for EA. Because of that, we cannot obtain the subcomplex KS from KL directly. So okay, so and remark that the action on the Y group action on the row space of lambda is freely and faithfully. The subcomplex KS is isomorphic to KGS for any S in row space of lambda and G in Y group. So because of that, we only need investigate the representative SIs in the row space of lambda. And the table shows that the Y group orbit types of S for E7 and E8 and the number of each orbit. For E7, there are only 3 types of S, and for E8, there are only 2 types of S. So then, but we cannot directly compute the KS from KR. So we decompose the KR, and this lemma says that here K omega is a subcomplex, not KS, a subcomplex induced by the set, this set, and this set made from fundamental by chamber and the Y group action by the isotropy subgroup. So then the Cox complex is decomposed by these subcomplexes, and Kg is G act on K omega. So, and the next lemma says that we only need we don't need 2 whole of these Kgs, but only we only compare the not total whole simple complex, but only the vertex. Yeah, we only need to compare the vertex. set of vertex. So, so this is the sketch for computing KS. As I told before, we cannot obtain the KS from KR directly. So first we compute the KG, and a piece of KR, and from this we can obtain a KSG. This is a piece of KS and KG. So we union this, we can finally obtain her KS. Then or is done. Unfortunately, it is not, because the KS is too large to compute the Betti numbers using by using the computer. Because of that, we have to refine the KS by removing the vertices. Before that, this is the example of the methods. So here, this is a K omega of type A3. And here, KSID is a piece of K omega ID, here this part. And here, KS 1,4 is a piece of K14. So we union all these four pieces, then we can obtain this KS. And so here, this is a link of V in K, and this is a star of V in K. And we want to using Weyl sequence. This sequence is exact, and A intersection B is non-empty, and so we set A to K minus V. This K minus V is really K minus V. Whole set of simplices of K original simplex K, but omit the vertex V. And here the set B is the star of V in K. So then we can obtain this result. Okay? So if the homology of link of V in K is trivial, then we can omit this while preserving the homology. By using this sequence, we can obtain this reduced simple complex from the KS. As shown, the number of vertices is dramatically decreased. And here, there are some propositions about the KS and KS hat. Proposition 1 says that KS1 and KS4 have two connected components, and the others are connected or connected. And proposition 2 says that here, these two cases of disconnected, its components are isomorphic to same component. And proposition 3 says that its KS hat vertex removed reduced simple complex are pure simple complex. And proposition 4 says that its component of this case, this two disconnected case, its component of KS1 hat is isomorphic to some induced subcomplex of KD6. This is very nice because we know about the or subcomplex of KD6, so we don't need to compute its Betti number. And proposition 5 says that here the KS4 has two connected components, and each connected component is isomorphic to KS3 hat. We can see that the number of vertices is exactly twice time. And so this is the result from the KS hat. So we can compute finally the reduced Betti numbers for each orbit, and here the number of orbits. So we can obtain the final result is by multiply the number of orbits and the results. So here this is the real toric variety. This is the Betti number, rational Betti number of real toric variety associated with the variable for type E7, and here is for type E8. And actually, we already know the Euler characteristic numbers of these, because we know the G2 Betti numbers of it. So, and here, so from this we can be more trust our results, because the alternating sum of our results are same with this. So okay. Thank you. This is